Hello, I'm audible. Hi. Hi, good evening, everybody. Thanks for joining in. Let's start with, I think, continuing the discussion on PCA. So, we'll be screen sharing in a minute. Yeah, so I think the presentation discussion will take me maybe an hour, maybe a bit more than that. Right after it, we can take up the practice assignment questions or any individual questions that uh, any of you might have. But let's start with this for now. Yes, I hope it's visible. Yeah. Okay then. So yeah, continuing the discussion with PCA. All right. So this is based on some, I think, recurrent doubts that I sort of heard even in the earlier term when I was taking the PA-ship in MLF, and I think in the instructor sessions also. So some quick exercises to address that. Okay. So suppose the original data points have 10 features. Before I continue, please somebody give me a confirmation that my screen is visible to everybody.
Yes, 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 really.
Okay, thank you. Yeah, okay. Suppose the original data points have 10 features, right? So although we can't plot it for obvious reasons, or we could, but we couldn't visualize it, the scatter plot would be in a 10-dimensional coordinate space or ambient space, right? So what would be the shape of the covariance matrix?
So 10 to 10.
10 cross 10, right? So just this is not going to be a very numerically intensive session, at least not this one. But the questions that I have included, this is sort of a very strong reinforcement that you should be able to tell these things like right off the bat. That if there are 10 features, right, the covariance matrix is going to be 10 cross 10. Why? Because covariance matrix is basically each entry in the covariance matrix is how one feature varies with another feature, one feature with another feature. So it's 10 cross 10 because there are 10 cross 10 pairs that are possible, including repetition, sort of like covariance of one feature with itself is just the variance of that feature, right? So you should be able to say these things right off the bat, right? Very good. So how many eigenvectors would the covariance matrix have? How many eigenvectors will a 10 cross 10 square matrix have?
So 10
10,
again.
10 again, right? Okay. So the eigenvectors of the covariance matrix are called the principal components in that data set. So suppose I wanted to retain only two principal components. This is, recapping stuff that we have seen, a bunch of times already. But A, B, or C, you can,
So A.
yeah,
A, sir.
A, yeah. You can also, speak up, or if somebody is maybe reluctant to maybe come on the mic, then you can write the answers. So interactivity is encouraged, right? We just remember stuff better when we're interacting. That's just the fact of it. So if you wanna, any interaction over any medium, right? Voice or text. Okay. So the best k-dimensional representation of a data point is given by the projection of the data point onto the subspace where it's going to be a hyperplane, right? Spanned by the k chosen principal components. And this subspace spanned by the k chosen principal components, so chosen according to this rule, chosen according to this principle, I should say. Principle, this is PLE, not PAL, right? But chosen according to this principle, right? If we are to choose, if you are to select only two principal components, then it should be the one with the top two eigenvalues, right? So the subspace, the hyperplane spanned by the k chosen principal components would be the representation subspace, the best k-dimensional representation subspace, but it's sort of understood, I believe. So here k is equal to 2. Now, what is the dimension of the coordinate space in which the projections live in?
So 10.
10. Very well. Is there anybody at all who has a doubt about this?
So can you please explain it? Here, what
Yes.
includes K?
Huh. So this is actually an important question. I mean, it's a trivial question, but it's an important question. So earlier I said that where did it go? Yeah. So basically that uh, we have the data point. We have a data point, let's say, and the data point is in 10D, right? Uh, I choose two principal components. I take the hyperplane spanned by these two principal components, and then I project onto this two-dimensional subspace, this plane, right? So after the projection, right? So projection is kind of ambiguous. Both the process and the product both are called projections, right? So it's a bit ambiguous, but um, the thing that we get after we project the original data point, right? Projection in that sense. What is the dimension of the grid in which this projection lives in? Is the question, does it make sense? I mean, how many numbers? What will be the shape of the tuple which would represent that point? Would it be a two tuple or a 10 tuple?
Two tuple because they will carry much more information.
Ah, yes. So I'm coming to informativeness in a second, but let's just think about projections, the space of the origin. As I'll get to your question, I have to ask, probe into it. But let's think about projections generally in math, right? Suppose, suppose I have everybody probably has some kind of a light bulb around them in their room, right? So just look up at the light bulb, okay? From the light bulb, draw a perpendicular onto the table, right? So that it basically lands perpendicular to the table. That is the point of incidence, right? So that would be what we would say the projection of the light bulb onto the right. My question to you is this: if you had to represent that point of incidence, would that point be in 3D or in 2D? If you had to give the coordinates of that point, would that point be in 3D or 2D?
3D?
Sir, point is
3D.
always 2D, sir.
That's not correct. You can point can be in any dimension. No, you can have a point in 10D also.
See, sir.
Po-
No issues.
So if you, Achan, no, it's a simple enough idea that suppose, suppose, suppose you have a ruler, right? The thing that we used in school. So a point along it, a point along the ruler, just along the ruler, right? It's sort of in 1D. right? And you just need a single, units are in millimeters or centimeters, right? You just need a single number to represent a point along the edge of the ruler. You just need 5, which would denote 5 centimeters from the start of the ruler, right? So that's 1D. 2D might be, for example, some point. Okay, 2D, I don't have a ready example right now because most of our interactions with 2D is sort of in a 3D space. But we live in a 3D space. So if you had to locate, if you had to give somebody coordinates for the point of incidence of that, of the line that you drew from the light bulb, it would be 3D, right? 3 coordinates, X, Y, and Z. And this is true for any dimension. And if you have 10D, you can have a point in 10D. It would be represented by a 10 tuple, right? It would be a tuple of 10 numbers, right? However, you denote maybe X, Y, Z, then maybe Greek alphabets, alpha, beta. It's not very standard how you go beyond 3, but yeah, 10 tuple. So,
Sir, does it
like,
go beyond 10?
sure, can go beyond 10. I mean, mathematics allows it. I mean, I don't know the physics angle to it, but mathematics allows us to talk about vector spaces of any dimension, arbitrary dimension, right?
Okay.
Yeah. But the physics reality of it is not within the purview of the present discussion. Perhaps interesting nevertheless, but not in the purview. But so this is what this question is about, right? That if I have data points in 10D, I have a data point in 10D, right? I project it onto a 2D subspace. Same thing. I have a point in 3D, right? The location of the light bulb, and I project it onto the table, right? Which is the surface of the table is kind of like a 2D subspace, right? Sort of like a 2D surface, but you can think of it as a 2D subspace or the floor maybe. So the original location was 3D. It had 3 coordinates. The new location is also in 3D. I've projected it onto a 2D surface, but that 2D surface lives in a 3D setting. So the projection also has 3 coordinates. Do we all agree on that?
Yes, the z coordinate is 0 there, means.
The Z coordinate would be 0. Yes, absolutely. Yeah, absolutely. But it's still there. I mean, it's not, we haven't dropped it yet. So the projection itself does not change the number of, the number of, the count of numbers in the tuple representing it, right? So if it was originally 10 tuple, the original data point, after you project onto a subspace, it's still going to be a 10 tuple, right? That's what I wanted to emphasize here. Okay, that projection itself does not change the dimension in which the point lives. The original data point and the projected data point, right? They still live in the same coordinate space. Although the projected data points now live in a lower dimensional subspace. They're all sort of all clustered together in a lower dimensional subspace. Here, a two-dimensional subspace. Okay. Okay, which sort of naturally leads to the next question, which is that the projections, that is, the new representations are still in 10D, right? The light bulb and the projection of the light bulb on the table, both in 3D. So where exactly did the dimensionality reduction happen, right? That's an important. So this is an open-ended question. The solution's right on the next slide, but this is an open-ended question. Would somebody like to maybe provide an answer for it? Basic linear algebra, very basic math 2 stuff.
So the vectors are linearly dependent.
What's that?
So the vectors are linearly dependent.
Which vectors?
uh, the new basis, the old basis vectors are linearly dependent on each other in this space.
Very well. Yes. And so,
Uh,
and hence, there is a certain redundancy in the basis set, right? So if set of vectors are linearly dependent means that there is a sort of redundancy, or which is basically that if you you could eliminate some vectors from that set. So you keep eliminating vectors from the old basis set. How many basis vectors would you finally stop at to span this representation subspace? If it's a two-dimensional representation subspace, how many basis vectors does it need?
so two.
Exactly, right? So in two parts. Any point in a subspace can be gotten as a linear combination of basis vectors of that subspace. Do we all agree on this? Yes. What about the others? What do we mean by linear combination, by the way?
So there will be representation and there will be coefficient.
Huh. So there will be the basis vectors and there will be coefficients on that basis vectors. Correct. Is there is there uh, is there a more intuitive way of sort of this is the math of it, the linear combination and sort of adding, but is there an intuitive sort of way to think about a linear combination? A linear combination is sort of in the geometric picture of it, it is a little bit like the basis vector is is a step, right? It's a step with a magnitude and a direction. And let's say I have a basis vector b and I do 5b. That means I take 5 steps along that basis vector in that direction, and each step length is the magnitude of that basis vector. See if you can visualize that. I have a basis vector b, right? It carries a direction and a magnitude. So if I say 5b, 5 into b, that is taking 5 steps in that direction with step length, the sort of length of that basis vector, right? So if I have b1 and b2, I take 5 steps, in the direction of b with step length, the length of b1. Sorry, when I 5 steps in the direction of b1 with step length, the length of b1, and add to that, if I said 5b1 plus 6b2, right? Yeah, 6b2 or 7b2. So we reach some place in the coordinate grid, right? If we take 5 steps along b1, and from there we take 7 steps along b2, right? So think of train tracks. This is an analogy that I think a former student brought up. I think that's a very good visualization for it. Think of train tracks. So 5 steps along B1 is sort of a train track taking you to a certain place. From there, 7 steps along B2, right? So this is one reinforcement of it, because we are sort of dealing with it visually also. Okay. So, if to reach a point in a plane, right, a 2D subspace, you need just two basis vectors, right? What that means is that you need two independent directions. You need two independent directions, and that's it. With two independent directions on that plane, you can reach any point in that plane, right? Just verify that the for let's say the standard choice would be one direction along the x-axis and another would be along the y-axis, but any two independent directions, right? Linearly independent. Okay. And the next question also, I think, ties it up, right? So how many vectors would a basis set for a two-dimensional subspace have? It's two, right? Okay. And therefore, this is where the dimensionality reduction is happening. If I project onto a 2D subspace, right, the projection itself is still the represent. I shouldn't say representation actually. The projected point, right? The projection that we get from projecting the original data point, that's still in 10D. Okay, it still has 10 numbers. But if it's in a two-dimensional subspace, then we don't need to keep the 10 numbers anymore. Right? We need to keep just two. And that is basically, the coefficients on each of the basis vectors for that subspace. Okay, this is sort of a very central concept, right? Without which it might not. I mean, later might not make that much sense. I mean, uh, not in my presentation, but later things in the course, right, might not make as much sense. Give me a thumbs up if it's all well and good. If not, please do raise your questions. Yes. Thank you, Ashish. Anybody else? Yes. Uh, Somebody raised their hand, I think. No, Amudapu, I haven't started writing yet. I will. I think we are well ahead of time, so I think we'll go on to solve some questions right after this. But yeah, anybody have any questions? No. Okay then. Yeah, because the thing that sort of comes later, right? Which is when you do kernel PCA, right? Um, there's this thing of uh, sort of recovering, right? Recovering. So if you kept the two numbers, right? If you kept uh, the two coefficients on the two basis vectors, you could recover the projection in 10 dimensions, right? But the essential idea in kernel PCA will be that you don't do that. You just keep the two numbers and use that as the representation, right? So two is too small a number. Let's, some bigger number than two. If it's 10D, maybe 5D representational subspace, right? So just keep five numbers, the five coefficients on the five basis vectors of the representation subspace, and then don't bother about reconstructing anything anymore. Those five numbers are the representation of the original data point, right? Those five numbers will not be interpretable anymore, as in if our original features were something sensible like price, height, weight, even the projected data point sort of has sensible features, right? It has sensible features. So if the original features, the 10 original features were height, weight, length, right? Sort of interpretable features, the projection is still interpretable, right? I hope that's pretty obvious. But if you get it down to these two numbers, right? The two numbers, the two coefficients and the two basis vectors, and then you just keep this and you discard, the original thing and the projection. These two numbers won't be interpretable in that sense. And this won't be height or length or anything sensible. The thing is that sort of, across the data points, there is a certain, the relationships between the data points is preserved in this two-number representation also. So what these relationships are, that's a kind of a non-trivial topic to get into. But here's one one of those things that might well be the case, which is that if two data points in 10D, right? If two pairs of data points, right? If one pair of data points were further than another pair of data points, so you have A, B, and C, D. If A and B were further apart than C and D in the original data points A, B, C, D, if A, B, the distance between them was more than C, D, the distance between, then this should be preserved in this two numeric system also, right? So sort of they should this comparative relationship should not be altered, right? And that sort of works out. This with PCA it sort of works out that if if in R10 A and B were further apart than C and D were further apart, then in this two numeric system the representations of A and B will also be further apart than the representations of C and D are further apart. I think that's pretty cool. Yeah, I hope I've been able to get it across. Okay. Yeah. Okay. So moving on. Here's an intuition for PCA, right? So imagine a game. Some friend of yours showed you a picture of an adult Alsatian dog in focus, right? So in the center of the picture, the primary focus of the picture, standing in a park. Now you have to sort of like Chinese whispers, right? You have to tell your other friend, some other friend, what you saw. But the catch is that you can only use one word, right? Naturally, then, to be good at it, you'd want to pick a word that would be most descriptive. Which among these options would it be? Black, dog, Alsatian, park. If you look at the question again, somebody showed you a picture. You have to describe the picture with one word only. Which of these four words would you choose?
C.
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 Correct. Yes. Any explanation why C and not B? Or why?
Because because I can identify that which kind of everyone knows that it is a dog, but to be very specific, it is Alsatian dog. It carries all what in one word everyone will understand that it's an Alsatian breed of dog.
Yes. And do we additionally have to say uh, that it's black?
Yes.
Are Alsatians of any other color? Are there Alsatians of any other color?
Yes,
Actually,
sir.
that's what I
Yes,
was.
sir. Yes, sir. Brown is
There
there.
are.
Brown is there.
Oh, but I think that defeats the point. But still, okay. Still, well, not entirely. I suppose that is new piece of information for me. But yes, Alsatian is. Uh-huh. Renee, your voice is very muffled.
Oh, okay.
Yeah. Yes, it's. I think it's a bit better now.
Is it better?
Yes, much better.
Yeah. So, if you're talking about a German Shepherd, I think
Yeah.
German Shepherds usually have black and brown, and I have not seen any breed as such that has different colors. So,
Yeah.
keeping that in mind, I think Alsatian describes mostly everything about it, like the fact that it is also black and it's a dog. It's very
Yeah.
specific.
Yeah. So it sort of covers most of the important things. And this, like I said, Alsatian was in focus. I like the the entity dog was in focus. So it's not the park which is primary. So it's not a picture of a park with a dog in it. It's a picture of a dog in a park, right? So it covers the important parts.
No,
So
here, according to me,
yes.
if that dog will be more appropriate because we are not classifying whether which type of dog it is, but in the picture we'll see that yes, it is a dog or this one. Correct.
Hmm. Hmm. But
But if you will
see,
classify again dog whether Alsatian or something, then we are
hmm,
again
hmm.
classifying that. Isn't it?
So that's a good thing, no?
No, it's a good
Your
thing.
your 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 yours you might be switching generality or generalness with descriptiveness, which is I get it. I suppose general models are most sort of descriptive, but here the more specific it is, the more descriptive it is, right? I mean, consider right?
Okay.
What do you say?
No,
So
very
it's
specific in that case. Yeah.
yeah. So the more specific it is, the more informative it is, right? And they wouldn't have to ask further, oh, picture of a dog, which dog? Like what kind of dog? They wouldn't have to ask. Versus it's not the other way around though. Because if you say Alsatian, they're not gonna ask an Alsatian cat or an Alsatian dog or an Alsatian, I don't know, rabbit, right? It's Alsatian is a dog, right?
Mm-hmm. Yeah.
Yeah. So it sort of covers the other things, but the other things don't cover Alsatian. Anyway, that's sort of maybe going thinking too much about it. But yeah, when I as as far as informativeness goes, as far as not having to ask follow-up questions goes, Alsatian is most informative, right? Okay. So yeah. Um, so if you answer Alsatian, then you intuitively understand what is meant by maximal informativeness, or likewise least loss in information, right? So, so as such, so just stepping into math for a second, as such, in the new representation of a data point with respect to the original principal components. So, so basically, right, if we have data points in a 10D, my covariance matrix will be 10 cross 10, right? I said right at the beginning that there should be something that should be a 1 second split second thing. If you 10 features, 10 cross 10 covariance matrix, it's gonna have 10 eigenvectors, right? Eigenvectors are also gonna be in R10. They're gonna be in 10D, right? So uh, covariance matrix is the real symmetric matrix, right? I should actually maybe included all this, but it's sort of more like a deep dive recap rather than strictly essential to the intuition of PCA, which is in focus. Covariance matrix is a real symmetric matrix. The real symmetric matrix has an orthogonal eigenbasis, right? That basically means that eigenbasis and orthogonal means that the principal components taken together represent principal component taken together constitute an alternate grid, like an xy grid. So the principal components, all the principal components taken together represent and constitute an alternate grid for R10 or 10D. Yes. So you can sort of change of this, right? We did in math too. So you can always change the basis. You can rotate the axis grid to sort of align with the principal components. That's the main thing. And when you do that, there are certain advantages. But so what is meant here, that in the new representation of a data point with respect to the principal components, you do a change of basis so that the principal components, all of them taken together. I haven't done, I haven't chucked away principal components yet. I've just done a change of basis. Each principal component is a feature, right? It's a you'll hear later that PCA, just in a next couple of slides, that PCA gives you new features, right? The principal components are new features, right? So right now, numerically, what that means is that if previously I had measurements along the x-axis and the y-axis and the z-axis, and these measurements were the numbers in my tuple, right? The x coordinate, the y coordinate, and the z coordinate. Now it's gonna be the PC1 coordinate, the PC2 coordinate, the PC3 coordinate, and so on. So, very trivially, relatively trivially features in that sense, right? These are the new axes in my, basis grid or axis grid now, right? But that's great for the math and arithmetic part of it. But don't think about the features in just a quantitative sense. So continuing from the earlier thought element that I introduced earlier, think about them in a qualitative sense, right? So features as in, dog, black, Alsatian, right? Qualitative sense. To get a feel for the idea, like I think get an intuitive feel for PCA. So think of each such qualitative feature as a principal component, right? Dog is a principal component. Black is a principal component. Park is a principal component. And you would agree that in order of importance, of informativeness, it's a picture of a dog first. Then we should specify that the dog is black. And then we should specify that the black dog is in the. Do you all agree on this? Yes. Okay. So, so yeah. So notice that I haven't included Alsatian here. That might be because Alsatian might not be a principal component. Might not be. So Alsatian sort of, says that it's a dog and it's black, but there might not be enough pictures of Alsatians for it to be a principal component. Of 500 images, maybe there are like 5 pictures of Alsatians. It might not become a principal component, which is not a problem. It can be expressed as a recombination of the existing features, like dog and black and big, maybe other snout, right? It can be sort of expressed as a recombination of other features, perhaps, but Alsatian itself might not be a principal component. But likewise, if it's only pictures of dogs, then dog might not become a principal component either, because all of the pictures are dogs, right? In which case, moving on to the next slide, but you have pictures of dogs, and maybe you have pictures of apples, no, maybe all pet animals, dogs and cats and rabbits, right? Then dog might become a principal component, right? Because it's sort of one and not the other two. Anyway, that's sort of loose speculation, but hopefully some of the intuition. I hope it makes sense. At least it's a sensible line of thought. Okay. So
Sure. So
yes, please.
is it indicating the loss? Like Alsatian, we cannot say as the first PCA. So is it indicating the loss that when we will reduce, we cannot get that Alsatian, but after that we can get the dog and the black and the park?
Huh. I don't know what you mean by indicating the loss,
Like
but
when we
basically
are
that,
reducing, like when
yeah,
we are coming to less feature, so we
yeah.
cannot get exactly the Alsatian part, but after that we can get the
Huh.
dog, black and pug. Is it due to the loss? Like
So you could say, loss in the sense of so
The
you
structure of
know
the data we had earlier, like
yes,
data we had.
yes. It would be lost in the sense of loss function, but loss in the sense of a missed opportunity. Alsatian, if you have just five Alsatians in a data set of 500 pictures of dogs, then it's sort of a missed opportunity. Alsatian is not that, I mean, most of the pictures are not going to have Alsatian as a feature, right? So it's not very, it's a loss in the sense of a missed opportunity. There's a better principal component that's possible, right? Right. So, yeah, that is about it. A principal component as a qualitative feature. So Alsatian as a principal component would not be a very important qualitative feature, right? Because most of the pictures are not of Alsatians. Yes?
Okay.
Yeah. Okay. So, yeah, so dog itself is a combination of more basic features. So, two pointy ears, two eyes, a snout, a wet nose, fur, right? So we are of course going to be thinking of it qualitatively, but I think we discussed in the last session and also in the instructor sessions that to a computer, an image is just a matrix of pixels, right? So basically, these patterns are going to come out in the, you know, how should I say, like adjacent pixels, right? If you have pointy ears, then there will be a pattern of adjacent pixels, right, which are darker than the other pixels around it, which sort of brings out the outline of an ear, right? Like, right? So maybe I'll ask me later or ask me in Discord. Maybe I'll share pictorial examples of this. But to a computer, an image is just a matrix, right? So these visual characteristics have very direct correlates in the numeric distribution in the matrix for that picture, right? So we are thinking of it qualitatively. There's no harm in there because it has a direct correlate in the way the numbers are distributed in the matrix representation of the picture. The picture as a matrix of you know uh, darkness or brightness values between 0 and 255, right? So all these things, ears, eyes, snout, nose, fur, right? These will very likely be captured as principal components, right? So more or less furriness, maybe shorter or longer snout, smaller or bigger eyes, smaller or bigger ears, more pointy or less pointy, right? So off the top of my head, those are five possible principal components, right? Along which measurements are sort of recorded. So yeah, these could be possible candidates for the principal components in a data set of dog pictures, dog images. But continuing with that analogy, it should then make good sense that each principal component is a linear combination of the original features, right? Um, uh, yeah, I think there's a bit of discontinuity here, but just take this as a fact for now. So just take this as a fact for now that each principal component has a direction, right? It's a linear combination of the original feature vectors, right? If your data points are stacked as rows, then the columns are the feature vectors, right? So each principal component is a linear combination of the original feature vectors, right? There is a bit of discontinuity here. I just realized. I was thinking about something when I wrote this. Anyway, I'll rectify that later. But the downside is that the new features. So this, thought experiment and this features in a qualitative sense, right? Quantal is another word I just want to throw out. Features in a quantal sense. Quantal as in an atomic sense. So that's a pretty good way to think about it. Dog, black, park. So in an atomic sense. But the downside is that these new features with PCA, and that is the principal components, they are generally not so neatly interpretable. That is, it's not so easy as to say that this principal component means ears, or bigness and smallness of the ears, bigness and smallness of the eyes, pointiness of the ears. It's generally not so neatly interpretable, right? PCA, one of the main drawbacks of PCA is sort of loss of interpretability. But this experiment still provides a very good intuition, as I hope it did. And it raises an opportunity to say that interpretation in any domain, not just in machine learning, it's an active process, right? It's sort of imposing an order onto chaos, if you will, right? Imposing an order when there was none. So it needs work. Sort of, you have to fit things into that mold, and that needs work. So it might very well be the case that if you have a data set and there is a high variance principal component, right? Then that principal component has an interpretation for it, which needs work to arrive at, even if the interpretation is not directly visible, right? So I think that's about it. That concludes the entirety of my presentation for today. Yeah. Any questions based on this presentation, or any questions at all? Otherwise, I can move to the practice assignment questions. Okay, then, if no questions, I'll stop screen sharing. Yes. Okay, so allow them to ask a question. Is the loss due to reduction? Could you? Yeah.
Yes, sir. That time I said it was. I typed that time when we were discussing that we can Atlassian cannot be a principal component.
It's not that cannot be. It's a loose intuition that I was trying to provide, right? But you have to realize that the principal components, principal components are features which are maximally informative across all the data points, right? So it's a little bit like this. If you have Alsatian as a new feature, if PCA outputs PCA wouldn't. That's the point. But suppose your algorithm output Alsatian as a feature, right? And you have 5 images of Alsatians in a dataset of 500. Then for the remaining 495 pictures, the measurement on Alsatian would be 0.
Yes.
So it's very low variance, right? For 495 pictures, the value of Alsatian is 0.
Yes.
Right? So it's not very useful, right? So in that sense, whereas if it was the other way around, that most, maybe not most, but if let's say maybe half your pictures are of Alsatians and other half of golden retrievers, right? Then Alsatian might emerge as a principal component, right? Yeah. Yeah, so that's the sort of a loose intuition that I was trying to bring out.
Yes, sir.
Okay. All right, that's it for loose intuitions, I think. Let's take a 2-minute break, and right after that, we'll start with we'll continue with practice assignment questions or maybe look at past year questions, right? Okay. Yeah.
Sir.
Yes. Okay, so I think Karthik sir has already started talking about, started presenting in his instructor sessions, um, Kernel PCA and uh,
Yeah, actually, we reached up to like why we need kernel PCA.
yes,
That was,
yes. Uh, so mainly two motivations, right?
Sir, I have a
Computational
small
cons.
doubt related to the previous one. Yeah.
Yes, yes, please.
Yeah. So my doubt was that if you have a data set of non-living things and a lot of dogs, and
Yeah,
then breeds of dogs like Alsatian.
just
So
start over once.
yeah, so if you have a data set where we have a lot of dogs and
Yeah,
non-living things, and under dogs,
non-living things.
yeah, like just normal
And in
objects,
what ratio? Just if you had to put some
like
numbers, in what ratio?
like it's mostly dogs.
Let's say 90% dogs or
Yeah.
80% dogs. Okay,
And then under dogs we have many classes of dogs.
with an equal distribution.
With an equal distribution, you can say. So my
Okay.
doubt was that will it be like the first principal component corresponds to the dogs.
Yeah.
Then the second principal component corresponds to the like the largest breed of dogs, followed by the other breeds. Will it be like that?
No, right? So,
Like my doubt is that will there be a hierarchy in the principal components?
the ordering. So principal components are the ordered, right? So there is a hierarchy in the sense that most informative, like some principal components are more informative than others, right? Given by the eigenvalues. So we retain the most informative principal components, the eigenvectors corresponding to the largest eigenvalues, right? But I don't think dog will be a principal component. I think if it were the case, right, once again lose intuition, but if it were the case, I think nose, ears, eyes, uh, face, fur, these might be principal components. Not
So,
dog though.
but they are the features, right?
Not the original features. No, the original features are the pixel values.
Okay, sorry.
The original, if it's a 28 cross 28 image, the original the original data points are in 784D 28 into 28, right? With each number being a brightness value, right? That's basically a black and white image is actually just a matrix of brightness values. Each pixel is a brightness value between 0 and 255. 0 is pitch black, 255 is pure white.
Okay, sorry.
Yeah. And if you did PCA, I think because of the recurrent outlines of eyes, nose, ears, snout, right? Because of the recurrent outlines, I think these might emerge as principal components, right?
Yes, sir.
If I had to put a uh, guess to it. Okay, but that's why I asked in the beginning. If you have pictures, not 80% dogs, right? Maybe 85% dogs, 25% cats, 25% rabbits. Uh, it's possible then that maybe dog might emerge as a principal component. It's possible, but then again, I don't want to go too much into that. The main point has gotten across that it's going to be the visual outlines that's going to emerge as the principal components. The visual outlines and not sort of the grouping of the visual outlines into dog or cat or rabbit.
Yes, sir. Got it.
Yeah. Yeah.
Uh,
Okay.
One thing, sir.
Yes.
Like as you know, the variance as the spread in any data set. So
Hmm.
I want to get an intuition that while preserving the maximum structure, that's what we are doing with the principal component lines, right? So we are trying
Right.
to preserve the maximum structure. So how the variance is playing an important role in that part, like that with variance we can preserve the maximum structure. Can't it be other factors?
So it is, uh, see, think about it this way, right? Um, yeah. Just 1 second.
Mm.
Uh, Actually, this is, I mean, I have a ready example. It's just I don't know that much about dogs, but some stray dog, right? The normal breed of stray dogs that we see, that is not very furry, right? Not very furry. Versus you have uh, uh, golden retrievers, you know, visibly more furry, right?
Mm.
Versus you have the dogs that what's it called? The Tibetan Lhasa, I think it's called, very furry, very hairy, right?
Okay.
So if you had to bring it down to a single feature, right? would you agree that this measure of furriness is a good feature? Because there is quite a bit of variance in furriness between dogs.
That would make sense.
Spread, right? Yeah.
Hmm.
So informative in that sense uh, versus maybe number of eyes of the dog. That has no variance. I mean, all dogs are gonna have two eyes, so zero variance,
Zero.
not informative at all,
Okay.
right?
Yes, the spread will capture the informations. Yes, yes.
Yes.
Hmm.
Yeah.
Got it.
Spread captures spread has informativeness,
Hmm.
right? When a feature that has a lot of spread has, it is going to be informative versus a feature that has no spread, like two eyes or 2 ears. That's not going to be informative because if you have done BBMS, it's the same idea of an identifier, right? So it captures a lot of information, means that it can be used to identify. If I say that a dog is, mildly furry, then it might very well be a golden retriever. But if I say that a dog has two eyes, well, which dog are you talking about? Right? I mean,
Hmm.
all dogs have two eyes, right?
Yeah, okay. So, can we conclude one more thing that the
Yes,
whole
please.
idea in the PCA, like
Yeah.
we are using, so it's very much dependent on the data sets that should have like a difference in the variance, visible difference in the variance.
Visible difference in the variance between the features.
Hmm. So the data set must contain a visible difference in the variance between the features, na?
The data set must have some variance. If
Hmm.
there is so a zero variance data set is all the data points are the same data point,
Hmm.
right? So that would be a zero variance data set, but it's not a data set at all. It's just, same data point stacked again and again.
Hmm.
Uh, right. But otherwise I don't, maybe if that's your question, then that's it. But otherwise I don't really get your question that well.
Like I wanted to say like is that the point where the kernel PCA came into role, like.
No, so kernel PCA came into role because of two reasons, primarily. First is computational considerations
Hmm.
that basically, Karthik sir must have discussed. I don't have a slide prepared for this, but if you have, uh, so in our course, we are using uh, data points stacked as columns. So that means the data matrix is D cross N, right? Data
Hmm.
points are stacked as columns. It was the other way around in MLF, by the way. In
Hmm.
MLF, our data points were along the rows. So, and that's how it's done. Implementation on computers, actually, that's how it's done. If you use NumPy or PyTorch, the data points are generally along the rows, right? But in mathematical derivations, I think perhaps this convention of data points in the columns is more common, which is why it's adopted in MLT. So in that case, if it's a D cross N data matrix, right, then your covariance matrix XX transpose by N, it's going to be D cross D, right? So now if your data points are 10,000 dimensional, right, which is not a huge number. If you were talking about images, right? If you have a 1080p image, that's 80 into 1080. That's the number of that's the number of pixels. That's the number of features, right? The dimension. So that is huge. That's what 10 to the power 6. So if you wanted to do PCA on it directly, then it would be order D cube. So
Hmm.
that's order uh, 10 to the power 18, right? So that's a huge amount of time.
Hmm.
Uh, if you're following along. Whereas if you had maybe just 10 or maybe 100 or 500 images, right? So if you could sort of figure out a way to do PCA on a 100 cross 100 matrix instead of uh, you know, that thing. So it would be a lot more efficient, right? Because this finding eigenvectors is going to be order d cube, right? When order uh, I see order d cube. Uh, that is correct. When the order of the cube of the dimension of the matrix, right? So if it's the original covariance matrix, that's d cross d, then it will be order d cube. And if you're doing kernel PCA, then the matrix is n cross n, and it's going to be order n cube, right? So if n is a small number in comparison, 500, n is equal to 500 versus d is equal to 10,000, that's going to be a lot faster, right?
Hmm.
So that's one motivation for kernel PCA, pure computational considerations. The other is basically that if your data is not linearly
Not
separable,
linear. Yeah, yeah. I
yeah,
was talking about it. Hmm.
yeah, then kernel PCA can sort of basically in a higher dimensional space, it can become linear. That's about it. So what might be a circle, right? What might be a circle in 2D, right?
Hmm.
If you added one more feature, it could become a straight line in 3D, right? Trying to think up what that feature might be. Uh,
Yeah. So,
yeah, but yes, this is about the gist of it. That if you shift it to a higher dimensional representation, right? Then it becomes linear, and then you can apply PC on it.
okay. So could you
Yeah.
just throw some more light on the like linearity of some data set? What is exactly mean like?
Linearity just means that it lives in a linear subspace, right?
Okay.
So
So,
linear subspace means that, for example, if all the points are arranged on a line, then that line is a straight line. It's not
hmm.
that the points are arranged along a circle.
Hmm. Hmm.
Yeah,
And one more thing, I think I got misunderstood as sir
yeah,
mentioned earlier that
yeah,
it has connection with the variance like when the data is in linear form like we will
yeah,
have
yeah.
different uh, lines where the variance will vary but some data points like as you mentioned like if we have circle and we have data
Hmm,
sets around that so
hmm.
if we find that the variance along any line will come up to be like same.
Yes.
So is this the role of the variance that where the standard PC has failed along with
Sir
the
must have.
computation, of course, along with the computation part. So
Huh, huh. So Sir must have mentioned this, right? That if uh, basically if your data points are sort of, so what is a circle? It just means that there's like an even distribution, right? There's a very unpatterned distribution. It's very evenly distributed, right? That's
hmm,
roughly
hmm,
what is meant by a circle.
hmm,
In which case, you know, the, eh, uh, earlier I said that uh, the principal components provide a new basis grid, right? You can rotate your existing basis grid to align with the principal components, and that has certain advantages. In this case, there will be no advantages, right?
hmm,
If
hmm.
your points are all aligned on a circle, then any pair of axes along any pair of axes, it's still going to be a circle.
We'll have the same structure always.
Yes.
Hmm, hmm,
Versus let's say your data points were arranged along a straight line.
hmm,
Then you could rotate the basis grid such that one basis vector aligned with this straight line.
hmm.
And that along that basis vector, you would have some variance. Along the other basis vector, you would have zero variance. And you would chuck.
Uh,
Yes?
The maximum variance will capture na, along that basis.
Ha.
Okay. Mm-hmm.
Yeah. Versus if you have a circle, there is variance in all directions. It's not just variance along one direction that we can discard one direction and just make it one dimensional. There's variance along all directions, right? So there's no advantage that can be gained by doing this basis rotation to align with the principal components.
There should be some like visible differences in the variances along different directions.
So yes, there should be some visible difference in variance along the different directions. Yes,
Okay.
absolutely. Yeah.
Now then a clear picture. Thank you, sir.
Yes. Yes. Most welcome. Okay. Any other questions? Otherwise, we can take up questions.
So I have a small doubt. Like when we take
Yes.
reconstruction error, right?
Yeah.
Do we have to divide by n?
Mm,
When we take reconstruction error for a set of data points?
yeah. I don't. Yeah. So that's more of a reporting thing because the the derivation won't change for it. I don't
Yeah, but in the
because
exam they ask for that purpose. For exam purposes.
in which case yes, 1 by n. Yeah.
We have to divide by n, you're saying?
Do divide by n. Yeah.
Okay, fine.
Just 1 second. Just give me 1 second. Let me confirm on that. Yep. Yeah.
Thanks, sir.
Divide by n.
And it's just sigma x minus norm of x minus w transpose x, right?
Yes. So I'll just share the link here. Karthik sir has some wonderfully prepared notes. You could use that as the last word on it.
So one more thing, like in the exam, right? The type similar to the assignment questions.
No, not very similar. So MLT, the course sector expectations from MLT go well beyond, go at least a good length beyond just competence with the formulae. So you are expected to have a very good intuition. So the questions are, uh, it's not just going to be plug in the formula, plug in the numbers, and that will be enough. Yeah, the expectation will be that you understand the algorithm well enough to sort of, uh, how should I say, uh, given a question, fit it, you know, fit how that algorithm applies to that question. Do that recasting or do that, fitting into the question on your own. So the graded assignments are, if from my memory, right, the graded assignments were significantly easier than the final exam. Significantly easier because the graded assignments were mainly numerical, mainly just testing basic understanding of it. The exam wasn't objectively hard, but just relying on the graded assignments to sort of evaluate or sort of anticipate the difficulty level of questions on the exam would be not very wise.
Yes, sir. And are there any like previous year papers?
Yes, there are.
Like,
There
where
are.
can I find them?
One second. I can share the link in the chat. So I believe the previous year papers are circulated informally for the most part. You'll find links to them on Discourse also. But there's a repository. There are multiple repositories. I have one of them bookmarked here, so I'll share that in the chat.
You can also check that ACE grid.
Okay. Yeah.
Sure, thank you.
Yeah. That's right.
One more thing, sir, where we can
Yes.
find that matcha file that Karthik sir has used in the previous session.
So that I can't say much about. That's entirely up to Karthik sir's discretion.
Okay, actually, during the
Yeah.
session we requested him to share us. We cannot find that file.
So maybe it will be shared in due course of time. I'm not sharing the slide that I presented today also right now.
Oh,
Needs a bit of polishing and then we'll share it. Maybe it's the same with him. I don't know though. It's
okay,
like I said, entirely up to his discretion.
okay.
Okay, so on the subject of past year questions, I think we'll look at past year questions once we are done with week 3, I think, or at least once we are confident with week 2 until sort of formally presented with the contents of week 2. So I'll keep past year questions after that because right now we might not be in a position to take on too many of them. But let's look at assignment questions for now. One second. One second. Okay, so last day we did practice assignment 1. Uh, and I think we finished that. Have you all looked at, so has everybody watched the week 2 videos? Then I can take on the practice assignment questions in week 2 also. PA2. Anybody? That's some mixed feedback there. Okay, let's see. Maybe I'll be able to clarify. Yes. Hmm. Just give me a minute. I'll be right back. Hello. Okay, so since there is mixed responses and I haven't formally presented week 2 contents yet, so I think let's wait till Tuesday, which is yeah, next session is on Tuesday. So yeah, let's continue on week 2 then.
Excuse me. You
Yes,
posted Mr. Karthik's slides, right?
yes.
It links only to one slide.
So I think if you do left and right, it will take you to the
Is there a left and right in that?
on the keyboard.
Okay.
Yeah,
Right. Thank you.
most of them. Okay then, let's conclude the session here today. I hope this has been helpful for your understanding of contents of week 1. Moving forward, we'll be focusing mostly on week 2 and beyond. So, hope to see you in the next session. Take care.
Thank you.
Thank you. Thank you for attending.